Hi, I'm Angelina Wang, and I will be presenting our work called Towards Intersectionality in Machine Learning, including more identities, handling underrepresentation, and performing evaluation. My co-authors Vikram Ramaswamy and Olga Russakovsky. Intersectionality was first introduced as a term by Kimberly Crenshaw to capture the unique harms that Black women experience, on top of that from being Black or a woman. It broadly refers to how different identities along different axes interact to produce unique forms of discrimination. However, despite its prevalence and importance, intersectionality has not been picked up much in the machine learning fairness field. Our work considers the algorithmic effects of discrimination against demographic subgroups by conducting empirical studies of 5 fairness algorithms across a suite of 5 tabular datasets derived from the US Census. To motivate the importance of intersectionality in machine learning, we begin by considering a typical fairness paradigm where we have a binary classification task of predicting an outcome of social importance. For example, whether someone will pay back a loan. It is important that classifiers which make decisions that affect people's lives are fair with respect to different demographic groups. One metric that we might find to be important in these settings is the true positive rate, which here would represent the probability that someone who will pay back a loan is actually given a loan. In this setting, there are a set of individuals in an arbitrary feature space, where the pluses represent individuals who will pay back a loan and the minuses represent individuals who will not. We could imagine a classifier learning a decision boundary like this and classifying everything to the left of the line as positive and everything to the right as negative. This classifier correctly classifies 6 of the 8 individuals, achieving an accuracy of 6/8. If we consider the difference in true positive rates as our fairness metric, then we see that the male group has a true positive rate of 1, while the female group has a rate of 1/3. This makes the difference in true positive rate 2/3. Now, we might imagine that we want to train a more fair classifier that minimizes this true positive rate difference. Our fair classifier drops the accuracy from 6/8 to 5/8, but improves the true positive rate difference from 2/3 to 1/3. However, when we disaggregate the female group by race, we see that the fair classifier has performed better for the subgroup white female at the expense of the subgroup Black female. Prior work has empirically shown situations like this across different tasks and classifiers, where fairness with respect to one axis of identity leads to unfair outcomes for one particular subgroup. While most fairness work thus far has not incorporated intersectionality, instead assuming the relevant demographic groups are only along one axis and binary, there's also been a large rise in excellent work recently that does include intersectionality. However, merely deciding to incorporate intersectionality is only the first step. In our work, we build upon this by engaging with the next texts that come up. There are many difficult considerations we need to keep in mind if we want to incorporate intersectionality in a meaningful way. Prior work has largely neglected these considerations, but there are substantive differences that set intersectionality apart in the multi-group setting and need to be considered. We begin by imagining a very simplified version of the machine learning pipeline, with the steps of data collection, model training, and model evaluation. In terms of data collection, we will need to think about which identities are relevant to include in the task. If we include too many axes of identities and numbers of identities along each axis, we risk having a computationally intractable problem. But if we include too few, we miss important intersectional differences in how different groups are treated. In model training, we need to consider how we can train a model when the various groups are likely to have a very small number of individuals as a result of having added additional axes of identity. And finally, in model evaluation, we need to think about how we will evaluate fairness on a large number of groups, since many of our existing fairness evaluation metrics are only designed for 2 groups, and the difference between them on some kind of performance metric. In this work, we concretely advise on how to address all 3 of these problems. First, I will explain the experimental setup we use throughout our work to provide evidence for our suggestions. When faced with a design choice, for example, which fairness metric to optimize for, we simplistically opt for the most straightforward choice that is most aligned with prior work in the space. This is because the goal of our work is not for exhaustivity in showing these issues will arise in every fairness setting, but rather that they do manifest in a generically adapted fairness setting with common algorithms trained on actual datasets. Thus, in line with prior work, we assume that the positive labels of each dataset are the desirable labels and adopt the notion of equal opportunity so that our fairness metric is the maximum true positive rate difference between 2 groups. For algorithms, we consider 1 baseline neural network and 5 fairness algorithms. Our training objective is a balance of soft accuracy, which is accuracy is measured on the probabilistic outputs of the model rather than binary outputs, and our fairness metric of maximum true positive rate difference. We use 5 datasets derived from the US Census, as proposed by Ding et al., predicting target variables like income and travel time to work. Returning to our pipeline, we first consider selecting which identities to include. Here, we find that a priori knowledge may be insufficient, and recommend combining domain knowledge with empirical validation. Domain knowledge based on which identities are relevant for a particular downstream task is important, but also insufficient for understanding whether, for example, two groups happen to share similar input distributions for one particular domain and would actually benefit from being empirically treated as the same group rather than separated. We consider a case study on the American racial group of Asian Pacific Islander. This group came about in the late 1960s, inspired by the Black Civil Rights Movement as part of an initiative to unify disparate groups. However, the forms of discrimination faced by individuals within this group vary greatly. We could imagine labeling each individual with the aggregate API label, but we could also consider breaking the group up into Asian and Native Hawaiian and other Pacific Islander. Further, we could consider continuing to break each group up into the constituent groups it is made up of, such as Cambodian, Hmong, Native Hawaiian, and Samoan. We consider this case study worth investigating because even though it does not strictly have to do with adding additional axes of identity, finding from this will help inform how to act in the intersectional case, because both scenarios involve one group, for example, Asian Pacific Islanders or women being heterogeneous due to an ignored label, for example, Cambodian or Hmong in the case of Asian Pacific Islander, or Black people or white people in the case of women. To consider the impact that considering the API group at different granularities may have, we consider a task of predicting whether the travel time to work is greater than 20 minutes. We train on 3 different settings where we consider the API group as one aggregate group, 2 groups, or 11 constituent groups. However, when evaluating, we are careful to evaluate on the most granular set of 11 labels that we have. On the x-axis, we have our 6 different algorithms, and on the y-axis, we compare a fairness metric of maximum true positive rate difference, where the lower the value is, the more fair the algorithm is. Here, we see that for a few of the algorithms, perhaps as expected given the known differences amongst the API group, training on the most granular set of labels indeed results in the most fair algorithms when evaluating on the same. However, surprisingly, for another algorithm, we see that training on a set of labels that does not have the most granular set of labels and only splitting API into 2 groups of Asians and Native Hawaiian and Pacific Islanders performs better and actually is the most fair across all algorithms and settings. What this tells us is that a priori knowledge of the heterogeneity of a particular group, in this case Asian Pacific Islander, is not always sufficient to know what kind of training procedure will be best. This domain knowledge will have to be supplemented with empirical evidence. It's also important here to note that any finding about how predictive different groups may be on a very specific task have no bearing on the societal meaning of these group delineations outside of the boundaries of this prediction task, and domain knowledge can of course override empirical evidence in situations where historical injustices have been known to result from treating a group as the same. The next consideration we look at is how by adding more identity labels, the number of individuals in each subgroup may be very small, and the challenge this could pose for model training, which may overfit to groups that are too small. Here, we first provide a warning that normative implications may disqualify certain existing techniques. We instead suggest a potential alternative through leveraging structure in the data, such as that people in different groups with shared identities may share more predictive patterns than those without shared identities. Typically, when there are groups with few individuals in a data set, one might use existing machine learning techniques for data imbalance, such as reweighting or generating synthetic examples. However, what this misses is that normative reasons can be sufficient to disqualify certain existing methods. For example, if they have harmful historical parallels. Generating synthetic examples has long been a technique used by machine learning practitioners to handle low data representation of a particular group. When the specific examples are generated in the facial image domain, the harmful parallel to blackface can be potentially sufficient to disqualify their use. As an alternative option, we might consider leveraging structure in the data. For example, if the Black female subgroup may share characteristics of the Black male subgroup that it does not with the white male subgroup in order to train more robust models. As we consider this option, it's extremely important that we keep in mind the point of intersectionality and how this means that each subgroup will experience unique harms due to their position at the intersection of interlocking systems of oppression. Thus, even if we show that we can leverage data in the structure to learn statistical patterns, this in no way implies any structure about the state of these groups in the world. We leave the experimental details for our paper. Next, we consider how we can evaluate fairness on a large number of groups. Researchers frequently use different variations of pairwise comparisons, such as the difference in true positive rate between the 2 groups with the highest and lowest values. However, we suggest using more deliberate contextual pairwise comparisons. We also suggest incorporating additional evaluation metrics that are better able to capture historical disparities. Typically in the literature, fairness is measured as the maximum difference of an existing metric, for example, true positive rate, either between 2 groups or between any group and the overall aggregate measure. As an example, in a setting where there are three groups that have true positive rates of 0.1, 0.2, and 0.8, the maximum true positive rate difference between any two groups is 0.7, which would be the fairness value for the setting. However, formulations like this ignore the values of the groups in between the maximum and minimum, such that a true positive rate distribution of 0.1, 0.2, and 0.8 would have the same fairness value as one of 0.1, 0.7, and 0.8. Additionally, it would not matter at all to the metric whether it was the black female or white male group that had a true positive rate of 0.1 as opposed to 0.8, which should make a difference to us. To get a look at what we might miss in practice if we use this kind of fairness evaluation metric, we consider a task of binary income prediction across our 6 different algorithms. We find that on this data set, the black female group, which we will call group A, has the lowest positive label base rate, and the white male group, which we will call group B, has the highest. We see that across these 6 algorithms, they all have different maximum true positive rate differences, some more fair than others under this metric. However, we might decide that it would be important to know how group A, which had the lowest positive label base rate, and group B, which had the highest, stand after such training. For example, which two groups it is that this maximum true positive rate difference is between. We note that the ranking we are comparing is in true positive rate and not predicted positive value. The predicted positive value is the proportion of each demographic group that is predicted to be positive. So a perfect classifier with 100% accuracy would show the same rankings for positive label base rate and predicted positive rate. However, this perfect classifier that is continuing to replicate the biases of the training data and reproduce this ranking between group A and group B would still be able to achieve equal true positive rates across all groups. However, we see that across all 6 algorithms, 5 of which have been explicitly trained with a fairness constraint, group A is consistently ranked low in true positive rate out of 4 total groups, and group B is consistently ranked high. Additionally, group B is always ranked higher than group A across all 6 algorithms. This tells us that even though the gap of true positive rate is being reduced, the algorithms continue to consistently rank group B above group A. We now return to a setting where we have 3 different groups that have different base probabilities of paying back a loan. Before we even train a model, we can rank the groups based on their positive label base rate, or the probability that individuals of this group have paid back a loan. Because historical injustices are often encoded in the data, we are likely to see that the most privileged group will have a higher base rate, and the least privileged group will have a lower base rate. Under the fairness notion of equal opportunity, we would like to know what the true positive rates of each of these 3 groups are after we train different algorithms. However, as we saw in income prediction, this frequently leads to a reification of this hierarchy in the rankings of the model's true positive rates. Instead, what we might hope to see is a shuffling that breaks up this hierarchy and does not consistently rank group A above that of group B and group C. Thus, a useful metric here would be the correlation between these 2 sets of rankings, and we could use the Kendall's-Tau metric or any other metric of ranking correlation to tell us this. The higher this correlation, the more the model is reifying existing hierarchies and entrenching disparities. Thus, we propose that in addition to metrics like maximum true positive rate difference, which may rank a set of algorithms relative to each other in this ordering, we also compare additional metrics that may produce an entirely different set of across-algorithm rankings. These different metrics should work in tandem to provide a fuller picture of how a model is performing for a particular task. Also at FACT this year, there's very relevant work that addresses this problem of measuring fairness across a large number of groups from a slightly different perspective. In this work, we address 3 considerations that need to be investigated when incorporating intersectionality into machine learning. We discuss which identities to include, how to train a model on groups with few individuals, and how to perform fairness evaluation on a large number of groups. Thank you for listening.